Welcome back, everybody. Last time, through Stokes' theorem, we saw how the fundamental theorem of calculus part 2 generalizes when we're integrating over a surface in space, something two-dimensional. Well, today we're going to bump things up a dimension and ask, how does FTC2 generalize when we're integrating over a solid in space, something three-dimensional? And so to start, let's just once again remind ourselves how we're thinking about the FTC2. If we squint, right, it tells us that we can integrate over something where we add up derivative information, or we can move through the boundary of that thing, adding up function information, and if we take a correct direction. And so our situation for today is we have some solid. So we have some kind of filled in solid chunk here, this region E. And so this is E is a solid three-dimensional region. And how the FTC2 generalizes is a result that we call the divergence theorem. And what we're going to do is we're just going to dive in, look at the formula, play around with a couple examples, and then talk about what's going on physically behind this theorem. And so to start, we're going to imagine that in 3 space we have a vector field. So right at each point off and on and in our surface, we have a green vector field vector, right? And if we want, we can think about these as showing us how a particular fluid is moving around in 3 space. And what the divergence theorem says is that, well, we can move through our entire three-dimensional region E, add up the information of the divergence of our vector field, or we can just move around the outside shell. So this S here, the boundary of our three-dimensional region, this is our outside shell of our E. Or if you'd like, E is the pillow and the pillowcase. S is just the pillowcase. And what the divergence theorem says is we can just move around the outside shell and do the surface integral for our vector field, right, adding up the normal components. And so here I claim that this does kind of match our squinty version of the FTC2. Over here on the left, the divergence of F, this is somehow derivative information. Recall the divergence of a vector field involves partial derivatives of the different components. And then over here we just see F, and so this is somehow playing the role of just our function information. With any surface integral for a vector field, we do need to orient our surface. Right? We need to choose a particular direction for our normal vectors. And in order for this equality to hold, the divergence theorem needs our normal vectors to be pointing outward. So here, each and every normal vector is going to be pointing towards the outside of our object here and not pointing in. All right, and so there it is in all of its glory. Let's look at a couple examples, and the first one is kind of just for fun. Let's look at the second problem from our last written homework. It had us just setting up the surface integrals for the kind of two pieces of this, I don't know, outer shell here. And so the work that we're going to do here is not going to help you for that one, because here we're actually just going to be able to compute what we would get, whereas on the written homework we're just setting up the integrals, doing the translation work. But here, notice that homework wanted us to compute the surface integral for our vector field f across our surface. All right, and from that homework, we wanted the outward facing normals in each one, and so this is exactly the setup for divergence theorem. And divergence theorem tells us that, well, we can swap that surface integral out for the triple integral, where we actually move, all throughout the inside of this thing. So this E here, right? This is S, and its guts, if you will. All right, so it's S and everything that S kind of bounds inside. And right there, similar to how we use Stokes' theorem and Green's theorem, right? These are translation formulas. Once we've translated, we just need to go through and work this out. And what's kind of cute is that here, if we look at our vector field, well, what's the divergence of this vector field? If you're having the formula, it's px plus qy plus rz, just taking the partials, adding them up. And so p with respect to x is 0. Q with respect to y is 1. And r with respect to z is -1. And so what we get is a big, fat, constant 0 as our divergence for our vector field. And so we can actually now very quickly work through this triple integral. It's telling us to march through our three-dimensional region E, add up the constant function 0, and that is going to hand us 0, right? There's no integrating that we need to do. We're adding up 0 across something, we're just going to get 0. So that's kind of a fun little application of the divergence theorem. The next example has a little bit more meat to it. Let's take a look. All right, so let's use the divergence theorem to compute the flux of the vector field. And recall it, this is just fancy language for the surface integral for that vector field. For this lovely vector field right here, here's our f across the surface of the solid, bounded by a cylinder and some planes. And so here in our notes, I've sketched the cylinder, y squared plus z squared equals 1. Right, in the yz plane, it's just the unit circle. And then, right, there's no x involved, and so that'll just get pushed forwards and backwards in the x direction, give us some infinite cylinder. But at this point, why don't you pause the video, see if you can kind of figure out, get a sketch of what our solid looks like here, and use the divergence theorem to swap out our surface integral for a triple integral and crank through it. Let's see how far we can get. All right, so let's talk about this here, getting a feel for what our solid looks like. Here we have our cylinder, the planes, x equals 0, right? That's just the YZ plane. And so we can just imagine that these little lines I had past that aren't there. And so we're cutting off our cylinder here. So that one's good to go. What about this plane, z equals 2 minus x? Well, if we wanted, we could take a look at what the graph of that would look like in the xz plane, right? Since there's no y involved, and this would look like a line just coming down with slope -1 and a z-intercept 2. And so with our three-dimensional setup here, right, this line, if we want to draw this line, would start up here at like z equals 2, and it would come down and hit the x-axis at 2 and then keep going. But now, because we're in 3 space, and this equation has no y involved, this line coming down diagonally is going to spread out backwards and forwards in the y direction and give us this plane. And so that plane is going hi-ya and chopping diagonally through our cylinder here and trying to sketch what that looks like. It's going to kind of give us some sort of ellipse, cutting that, and so putting all that together right there is our lovely sketch of our solid E. Right? So E would be the region that this thing bounds, three-dimensional region, and S is just the outside shell. All right, so now we have a picture of what we're talking about. So the surface integral by divergence theorem, we can swap out for a triple integral. And this is actually usually the way that we use divergence theorem, just because triple integrals don't require us to write like parameterize things and choose normal directions and all of that it's involved with the surface integral for a vector field. So triple integral is often cleaner. And once we've done that, we've used divergence theorem, right? And that's where it happens. And so now this triple integral here just becomes our world. And so we just need to figure out the different pieces, the divergence of our vector field, and then set up our limits of integration and crank through it. And so let's work through that. The divergence here of our vector field, just using our formula. So our x components partial with respect to x. The x will just go away. We're left with 2y squared. Y components with respect to y. We're just going to get 3z squared. And then our z component with respect to z. The natural log weirdness goes away. And we get so the 3 will come down and cancel, we'll get minus z squared. All right, and so notice that happily we do get a little bit of cancellation going on. The 3z squared minus z squared will give us the 2z squared. And so that'll be what we plop in here for our divergence. Now, once we have that, we have our function that we're integrating. We just need to set up our limits of integration. All right, so looking at our region here, right, our three-dimensional solid, what sort of coordinates do we want to use to describe this? Looking at this, what stands out to me, if we move in the x direction first, we're always starting at our x equals 0 plane, ending at the slanty plane, and our shadow in that direction is going to be a nice, clean disk. And so I think cylindrical is going to be a clean way to think through this, right? Let me add on to our picture here, the notes I just mentioned, right? So if we pick a YZ and move in the X direction, we're always starting at X equals 0 and then moving all the way through and then pop, coming out at this slanted plane, right? And that's going to be true no matter where behind this thing we are starting. And what's the shadow going to look like? Well, it's this, this disk here in the YZ plane, our unit disk, in fact, we can see just coming from our cylinder. All right, so putting that together. We're always moving X from our X equals 0 plane to our slanted plane, which is, if we need to solve for X, is X equals 2 minus Z. And then the shadow here, it's unit disk, so R equals 0 to 1, theta from 0 to 2 pi will move through that whole shadow. And so we get our dV over here as R dx dr d theta. And nicely, if we look at our function, it's playing well with cylindrical as well. We can take these common 2's and pull them out. And what we're left with is y squared plus z squared. That's going to collapse nicely as r squared, right? Just using our polar formulas in the YZ plane, right? And so in this case, all right, y is horizontal, we're thinking of it as, and z is the vertical. And so a little bit of translating left to do. It's y squared plus z squared. That becomes r squared. And then looking here in our limits of integration, all is well except for the z right here. Right, our three variables are x, r, and theta. And so we're going to take that z and swap it out for what it is from our coordinates. And with that, we have a nicely set up triple integral. All that's left to do at this point is start cranking through our three integrals. I'll leave the details for you, but at the end of the day, I'll end up with 2 pi. All right, so that is a little bit more substantial of an example of using the divergence theorem. Let's switch gears and think about what's going on physically behind the divergence theorem. And it turns out that it has a very similar idea to Green's theorem and also Stokes' theorem as well. So let's first remind ourselves of what's going on with Green's theorem. Right, we had a region in the plane, and Green's theorem looked like this, and our physical interpretation was qx minus py is handing us the circulation of f at a point. Right, so the idea is if you pick a particular point, maybe you can do a little square around it. Looking at the circulation of the vector field, and I guess I should add into this picture, right? We do have a vector field, so we got green vectors, zipping this way and that. There they are. And how this played out is if we kind of inside this region, if we put some grid inside this region, well, if we kind of move through and say compute, the circulation around say this point and around this one over here, let me do a different color. Well then, right here on this common side, from the square on the left, we're moving up, but the square on the right is moving down. And so our information there is going to cancel out, and all these common sides disappear, and right in the limit, we're left with just moving around our outside edge and computing the circulation of our vector field there around our boundary curve C. And what I claim is that this is exactly what's happening, but instead of circulation, we're thinking about divergence. So divergence of a vector field, I claim that the idea here is that we can kind of pick a point and slap a little box around it and look to compute how our green vector field vectors are showing us how our fluid's moving around. Are passing in and out of that little box around our point. And if you take that and weight it appropriately and kind of collapse it, what pops out is the divergence. And so this divergence is kind of showing us how our fluid is wanting to move in and out of these little boxes. And so if we take our three-dimensional region here, kind of fill it up with these cubes, we'll get something like this. Right, and over each of these boxes, right, the divergence is looking at the normal components across each of these sides. So we have these normal components that we are looking at are each of these sides. And so we got one kind of pointing that direction and one pointing down, and we have one kind of pointing behind as well. But notice, for this cube right next to it, it has these vectors as well. It has one, pointing up, and it has a normal vector here pointing this direction, and one pointing down and one pointing out, etc. But like we saw above, when we have a common side, notice our pink vector and our blue vector are directly opposing each other. They're going opposite directions. And so the normal components from our green vectors that they're grabbing there are going to cancel out. And the information here that we're getting from all the common sides of our cubes disappears. And we're just left with, at the end of the day, the normal component information along our outside shell. And that's exactly what the surface integral for our vector field computes. Right? It goes along that surface and computes the normal components of our vector field. And so what's exactly happening with the divergence theorem is just another kind of manifestation of this situation where the info that we're adding up from these common sides is canceling out, and we're just left with adding up some information around the boundary. And so something that perhaps mathematicians like to think about is, from all these different theorems, Green's theorem, Stokes' theorem, divergence theorem, they have this similar flavor, this similar interpretation. Might that be coming from somewhere? Might there be some kind of higher, more generalized theorem that these are all kind of stemming from, like branches from a tree? And the answer is yes. It turns out that, in fact, all of our generalizations that we've seen of the fundamental theorem of calculus part 2 are unified or are seen as special cases of a particular result in a general context. So I just want to say just a few words about this because it's cool. So first of all, just looking at this, it kind of looks like our squinty version of FTC2, right? integral over something looks like maybe some derivative information, or integrate over the boundary of that thing of some just normal function information. And so this equation here takes place in the land of manifolds. So these are things that maybe globally have some interesting structure, like the Earth, right? But if you don't venture too far, if you just look a little patch of the Earth, right, we can approximate that patch of the Earth with something flat, right? And this is exactly what we do when we look at Google Maps. We're not thrown off by the fact that there's not a curvature going on with our screen. Right? And so this is the idea behind manifolds, things that locally look flat, but maybe globally have some interesting structure to them. And what this says is we can either integrate something over an orientable manifold. Orientable means it has these well-defined sides. Or we can integrate over the boundary of that manifold this thing. And so that this omega here, this little W looking thing, is what's called a differential form. And I'll say some words. It is a section of the cotangent bundle. Wait, I didn't say it right. It is a section of an exterior power of the cotangent bundle to our manifold big omega over here. So it's this thing that has this definition that has layers upon it. But it's a thing, okay? And it turns out that you can somehow make sense of taking this thing's derivative. This here is omega with the exterior derivative applied to it. And so here, this is somehow playing our derivative information. And it's this general result that in all of our different setups becomes all these generalizations that we've seen. All right, that's it for today. Good work, everybody. If you have any questions, post those to Piazza, and I'll see you next time.